Hello friends, my name is AJ and welcome to lesson 2 of the Data Structures and Analysis series. In this video, I'm going to introduce a very important concept known as Big O notation. And this is the way that we analyze the efficiency of our code and of our algorithms. All right, so without further ado, let's get started. Okay, now the first thing is you might be wondering, well, why do I even need to do this, right? And you have to realize that whenever you're working with code, right, not all code is created equal. I mean, you can have a problem that you're trying to solve with your code, but there would be dozens, if not hundreds of ways to solve that problem, right? Hundreds of algorithms, hundreds of ways of organizing and writing your code that can actually accomplish a goal that you have, right? However, in larger scale problems, right, where we're working with millions and millions of inputs and we're trying to, do something in a very quick and efficient manner for actual users, we need a way to tell which algorithms are actually going to be better than others, which will be more efficient than others, right? And we can do this essentially using this idea of time complexity and actually trying and comparing the efficiency of one algorithm to another. Right? And the first thing that we need in order to do that is we need a way or a notation to essentially describe what the efficiency of one algorithm is versus another algorithm. And this is going to be known as Big O notation. Right? So I'm going to write this out here. So we have Big O notation. And again, this is going to be our notation that we're essentially using to describe the efficiency of an algorithm. And we do this using this O of something, right? So we have this O right here. I'm actually going to kind of write this a little bit bigger. So we have this O, and then we have something inside, right? And if you want to think about this, right, we usually put in some sort of parent function that describes the relationship. So this is going to be a parent function, right? So this is going to be a parent function. And this is going to be a math, right? A math function that we're essentially using to describe the efficiency. However, what are we even trying to describe, right? What do we mean by efficiency? What variables are we comparing? And essentially, what we're doing is we're going to be comparing the number of inputs into a function. So I'm going to be writing this out here. So you have x, or in this case, we call it capital N, right? So N, this is going to be the number of inputs, right? So this is going to be number of inputs, right? This is going to be the number of inputs into your function, right? And then we're going to have t, which is going to be the time it takes, right? The time for the algorithm to run. So the time it takes for the algorithm to, I'll write out algorithm to run, right? So you have n, which is the number of inputs, and then you have t, time it takes for the algorithm to run. And essentially, right, the efficiency that we're going to be looking at is going to be, well, how does the time increase in relation to the number of inputs that we have, right? Because if you think about it, let's say you have an algorithm and then you put in 10 inputs into the algorithm and it, almost instantaneously spits out an answer, right? Well, even if you use various algorithms, you'll find that the time it takes for that algorithm to run will be relatively the same, and it will be really, really fast because the number of inputs are really small. However, what if you increase the number of inputs, right? Increase the amount of data that you're actually working on in the algorithm, right? What if you increase it to 100 inputs, 1,000, 10,000, 100,000, and millions of inputs, right? Because that is actually how big a lot of programs, in larger software and larger companies are actually, working with, right? So at that point, when you have millions of data points, you'll actually find that some algorithms will actually take longer to run than others, some much longer than others. And that really depends on this relationship between the number of inputs and then the time it takes, right? So essentially what we're trying to do is we're trying to describe this function t of n, right? T of n. Because this is going to be if you think about it, the time it takes, I'll kind of put it right here, right? This is going to be your y-axis. And then your x-axis here is going to be the number of inputs in your program, right? So in this case, right, we will have t of n, right, which is going to be kind of this function that we're trying to describe, right? And we want to represent this using a parent function. And that's why we take this big O, right? And then we put a parent function inside of this, right? And what do I mean by a parent function? Well, a parent function is going to be just a basic function. And I'm going to show that. So I'm going to say f of x here, right? F of x is going to be my parent function, right? So this is going to be a parent function. So parent function. And well, what are the parent functions? If you remember from either an algebra class or maybe even pre-calculus or higher, a parent function, right, it consists of something like x, right, or x squared, right, or 2 to the x, right, or log x, right? These are all examples of parent functions, right? They are kind of the base functions that represent the relationship between two variables, right? So if you notice here, when we're actually going to be describing this efficiency, we're not really going to be caring too much about, for example, if the efficiency, or I guess the time it takes for the algorithm to run is going to be like, 2n squared plus 4, right? We don't really care about the specifics. We're not trying to really calculate, numerically exactly how much time it takes for an algorithm to run. Rather, we want to know essentially the relationship, right? The relationship between the number of inputs and the time it takes, which can essentially be a kind of, simplified and abstracted down all the way to the parent function, right? So using kind of this math term here, we can essentially say that this is our basic formula for our kind of big O notation right here. I'm going to see if I can kind of draw this box. Yeah, that is essentially going to be our main our main thing, is that the t of n, right, what we're trying to describe is going to be equal to this O, and then you put a parent function inside of it. Now, when I'm actually talking here about this big O notation and this complexity, right, what I'm really referring to is going to be the upper bound. And I'm going to show that kind of in the, in the next picture here too. But if you think about it, right, you can have an algorithm, right, that takes in a whole bunch of inputs, right? But oftentimes you don't actually need to use all of those inputs. Sometimes we'll be able to solve the problem by, using only a few inputs and not all of them, right? If you think about this, for example, let's say you have a list, right? Let's say I have a list of values from 1, 2, 3, 4, 5, 6, 7, right? And I'm trying to find the value 4, right? Let's say I'm trying to do a find, and I'm trying to find the value 4, right? Well, my algorithm is going to jump from all these values. It's going to start at 1, right? It's going to kind of start at 1, and then it's going to jump to 2, and then it's going to jump to 3, and then it jumps to 4, and it's like, oh, I found 4, right? I found 4, and so now it's probably going to return maybe the location, which if I was counting, right, this was 0, 1, 2, 3, right? It's at the index position 3, and now I'm going to take this value and I'm going to return it. However, if you noticed, in this particular, find algorithm that I just showed, we did not actually run it on all the values. We only ran it on a few of the values, right? And that's something that is really important to think about, is that most of the time with your algorithms, you're not actually going to be using every single input value, right? However, what if you did use every single input value, right? This kind of notation, this big O notation, is essentially finding that, that complexity if you use all of the values. So it's the worst case. If you actually were to run your function, right? If you actually were to, run your function and see the time that it took, it's generally going to be somewhat less than this, this parent function that we write. Right? So for example here, I'm actually going to kind of take this and I'm going to minimize. So it's very small, but I'm going to move it down here just so that you can keep that in mind. But I'm also going to be erasing this x, and I'm going to be replacing this with n. Because again, we kind of referred to here that n is really our variable, right? It is going to be the number of inputs. That's going to be kind of the synonymous thing to our x value. So I'm going to replace all these things with n, just because I think that will make a bit more sense and keep everything together. However, what I'm referring to down here is the fact that, if I were to take then any value, so let's say I, take if I'm actually trying to find this t of n, right? Because this is going to be, right, this parent function is going to be an upper bound, right? It's essentially referring to the time it takes if every value is essentially going to be, checked in some way or is going to be used in some way. then we can say that the actual time that it takes is going to be less than or equal to this f of n, right? It's going to be less than or equal to our function here. And also, in addition, you can add you can add some sort of c here, right? Because remember, we're talking about a parent function. And so when we're talking about a parent function, we're essentially going to be, there will actually be, like I said, there might be, for example, 2n plus 3, but is really just, kind of the relationship as shown, but not the actual value. So the c f of n here, this random constant that I'm throwing in front, kind of essentially, describes that any additional change that we may make. All right. So now this is essentially going to just describe, that really this is an upper bound, right? All this is saying is that this time complexity, or this function that we're finding, is really going to be an upper bound of the amount of time it takes. So this is going to be the upper bound, right? This is what this means, essentially, this entire thing. It just is the mathematical expression saying that this value is an upper bound, okay? Now, there are various different time complexities, and pretty soon you'll actually see, actually finding these, this big O notation for various code chunks. And I'm going to be showing you how to do it because, it's actually a pretty simple process that you have to follow. But I'm going to now jump down here to the next page, which is going to be essentially comparing our big O complexities, right? And remember, our big O complexity, if I write down here, right, if we say that a function is, I don't know, O of n squared complexity, we're essentially saying that, well, the parent function, the relationship between the number of inputs and the time it takes to run is going to be n squared, right? And so we're really describing just a bunch of parent functions. So if I'm comparing my big O complexities, well, the first thing you might have is going to be simply a very nice straight line, right? Just like that. And this is going to be O of n. You may have guessed that. O of n, right? Because this is going to be a linear relationship between our, problem size or number of inputs and the time it takes for it to run, right? Now, in some really nice cases, you might have O of 1, right? Where you're essentially saying that, well, as my input increases, the time it takes for my function to run is always going to be constant, right? There's essentially going to be no change in the time it takes to run. Right? And obviously, this is the best case. This means that your algorithm is great, right? You can have millions, even billions of inputs into it, and it's still going to return a value essentially at the same time as it would if it only had one input, right? So that's really good. Most of the time, this is not really feasible or practical, right? And kind of not really a goal that we should try and get our algorithms to, simply because most of the time, it's just not going to work, right? Another one, which is great, is going to be this one. I'm going to see if I can draw this out here. Whoops, I deleted everything. Let's see if I can draw this out. It might not be very good or completely right, but this is going to be O of log n, right? This is going to be O of log n, right? And I believe that this really should be, I should probably be drawing this a little bit better. I don't know if I'll be able to here. So kind of, yeah, that's pretty good. O of log n is another kind of time complexity, which is great. We would love to have O of log n a lot of the times that we make functions. Again, it might not be feasible depending on the problem you're trying to solve, but it's a little bit more reasonable than something like O of 1. And you'll find that a lot of algorithms that you'll run, even in this series later on, will end up being O log n, especially when you're working with various data structures. And I'll be showing all of that a little bit later too. Right? And now what I can do is I can look at, well, what are some other ones, right? Now we're getting a little bit greater than O of n, so it's beginning to get a little bit more inefficient. And what I mean by that is that for all the problem size, right, as I increase the number of inputs, the time it takes to run is going to be greater than a linear amount. And so the first thing I can probably draw here, and I can do that like this, right? This is going to be O n log n. Right? So this is going to be a bit greater than, O of n as a complexity, right? Oftentimes it is if you're taking an O, an O log n algorithm and running it n times, you'll end up with O n log n, right? Another one that's decently common is going to be, right, O of n squared, right? O of n squared, you can tell this is worse, right? As we're going above, and I can kind of highlight here, maybe. Yeah. As we're going above this O of n, right? We're getting worse now in the algorithms. We're getting less and less efficient. I guess I can draw that, right? So as we go below, so this will be, right? So if I go down this way, this is going to be more efficient, right? This is going to be more efficient. And then as we go kind of this way, greater than O of n, this is going to be less efficient, right? But lastly, another parent function, which is the worst one. Well, there are worse, like there are ones that are worse than this, but this is kind of one of the worst ones, is going to be O of 2 to the n, right? This is going to be kind of this exponential relationship. And you can tell that anything, especially these two, right? Especially kind of when you have this, when you have this, let me see if I can, when you have this kind of O of n squared and O of 2n, right? These two things right here, that is pretty bad, because as your inputs are increasing, your time is just going off the charts, right? So, but this is a good kind of comparison of all these complexities. And when you're going to be kind of looking at algorithms or comparing algorithms, you're really going to be looking at these, right? You're going to say, well, okay, well, my one algorithm, let's say algorithm A is going to be O of n, but then algorithm B is going to be O of log n. Which one's better? Well, it's going to be algorithm B, that's O log n, right? If I'm comparing, another two that are like, O log n, or sorry, O n log n and O of n, well, the one that's O of n is going to be faster. It's going to be more efficient. And so that's where the comparison of these kind of, time complexities and these notations here is really important, because that allows you to determine which algorithms are more efficient than others. Now let's jump into some code and actually analyzing some algorithms here. And we're going to be kind of calculating all of these big O notation out, right? We're going to be finding the big O notation for all of these algorithms. Well, this is a simple kind of, you're saying integer, A. And remember, all of this, by the way, is in Java. I think this is the first lesson where I'm actually looking at code. The last one I may have as well. But again, this is in the Java programming language. All of the concepts here can be applied to all other languages as well. But we're just creating a variable A, which is 2 plus 1, right? Well, what are my inputs? My inputs are essentially, well, there's actually no inputs if you think about it, because everything is contained, right? This 2 plus 1 was already written, right, as part of the program. There's no variables here. So in the end, even if I were to put like a million inputs into a function that included this line of code is always going to run at the constant time, because it's going to essentially be, arithmetic. We're doing 2 plus 1. So when we're finding the analysis, or the kind of the relationship between the number of inputs, right, and our time, if you remember this, right, you have t and n. Well, if I have, if I'm just doing arithmetic, my time will always remain constant no matter as many inputs I might have in this function. And so we can then define, we can say that the kind of the efficiency or the complexity of this algorithm will simply be our really nice O of 1, right? And again, this is because, and I'll be careful not to write exclamation point close, because, I'm not trying to write any factorials here, but O of 1, this is going to be very nice, and this is going to be because this is arithmetic, right? So whenever you're doing arithmetic and you have like no variables, it's going to be O of 1. All right? Hopefully that kind of makes sense, right? If I had a function, I'm just going to kind of write this out again. Like if I had a function, A that takes in, it takes in a list, let's say. So let's take, it takes a list of integer. Sorry, I want to kind of write that a bit better. A list of integer, right? And then I'm just going to call this L. And then inside of here, I still had int, A. In this case, I'll call it B because I named my function A, equals 2 plus 1, right? No matter how big this list is, no matter how many inputs I have, this is always going to run the same amount of time, right? That's essentially what we're describing here. Now looking at the next one, this is again using now a function notation. So I actually have code in a function, right? And we have one input, right? So we have one input into our function, one input, and this is going to be our variable x, right? So one input is going to be variable x. And the only thing we're running in this function is going to be this print statement right here, right? This is going to be a print statement. And in this case, what do you think is going to be the kind of complexity of this algorithm? Again, think about this graph, right? Between our number of inputs, right? Our number of inputs and then our time it takes, right? Well, in this case, we have a single input, right? And we're essentially printing out a value, right? So printing out a value is simply going to be running the same amount of time no matter how many things I put in here, whatever value I put, right? There's also a very important distinction which you have to realize between the value of a variable and the amount, right? This n is referring to the number of inputs, not a big value. If I put in 1 for x, like if I said x equal to 1 or x equal to a million, right? The n is still 1 because there's only one input, okay? So my number of inputs is not changing, and my print algorithm or my print ln function is going to always run the same amount of time no matter what input I put. So our time is going to be constant, right? Our time is going to be constant. And so therefore, we could say that again, this is going to be O of 1. And that is very nice, right? Very nice. And again, this is simply because there is only a single input and our println, right, runs at a constant time. All right, now we're going to look at something interesting, right? So now we have this if statement, okay? Well, I'm going to assume, I'm just going to kind of write some stuff out here, and we'll actually be looking at a block of code which will produce O of n, but let's just pretend that my do something is going to be O of log n time, and do something else is going to be O of n time, right? Where essentially, you don't know the implementation of these two functions, but we're going to assume, or methods, but we're going to assume that these two methods have these two time complexities, right? So how do we analyze this? Well, when we're actually using if statements, there are three things that we're checking, right? Because remember, we're talking about the worst case time complexity, right? Worst case, meaning that, what is the worst possible combination of all these times that we can have in order to have the worst, overall efficiency? Well, there are three things that we check, right? Or three things that we can run. The first thing that we run is going to be this, right? Our condition. So the first thing that we can run is our condition. And this is the first thing that really contributes to our complexity, right? Then we could run our if block, right? We could run our if block, which is going to be right here. And then third, we could run our else block, right? Which is going to be right here. And in this case, how do we determine the complexity of this if statement? Well, we're going to use this basic formula here, which is not necessarily even that big of a formula, but we're essentially going to find the max. We're going to find the worst one out of all of these three components. We're going to say, well, what is the max of the O condition, right? What is going to be the time complexity of the condition? What is going to be the time complexity of the if block, right? And what is the time complexity going to be of the else block? And that is going to essentially determine what the overall complexity of this if statement is going to be. And I should close my max function. Well, we can say very clearly that, if we just look at this, well, x less than 4 is, again, and is kind of like the arithmetic one, where it's, no matter what inputs we have, it's always going to run the same amount of time because it's a comparison. So this is going to be O of 1. So I'm going to, I guess, put an arrow. So our first thing that we were checking was our max of our condition, which is going to be O of 1. Then what is our if block? Well, there's only one thing in our if block, and it's going to be O log n, right? Our entire if block is going to run O log n time. So I can write here O log n. And then our else block is going to be this O of n, right? And so now if we compare O of 1, O of log n, and O of n, and remember, I can jump all the way back to here, right? We had O of 1, which is our condition, O of log n, which is our if statement, or our if block, and then we have O of n, which is our else block. So what is the least efficient? What is the max? Well, just by looking at this graph, you can tell that O of n is going to be the least efficient. So down here, I can say that this is going to equal to an overall time complexity of O of n, right? And I'm going to make this green just so that it kind of shows that this here is going to be O of n, right? And if you just think about this logically, this actually makes sense, right? Because, there's two different ways that I can be running this algorithm. I can either be going through the if block or I can be going through the else block, right? Well, in the worst case scenario, I'll end up in the else block and I'll have this O of n, this O of n time that I'm running. And that's going to be less efficient than the O log n. So, just if you compare both potential outcomes depending on what the condition really is, because we don't know what the condition is until runtime. So we can't determine immediately, well, are we going to always go to the if block or always go to the else block, right? However, we just look at the two, we can say that, well, if we end up in the else block, it will be worse than if we end up in the if block, right? So the overall complexity of this, remember, this is worst case, right? The worst case complexity of all of this, like this entire if statement, is going to be O of n, because in the worst case, you'll end up in the else block and running all the code here. All right? Now we're going to go into a loop, and loops are very interesting. So I'm going to start off by essentially saying that my O or my do something here is going to be O of 1, okay? So let's just take a look at this, right? This for loop. Right? I am going to be incrementing from 0, right, to 1, to 2, to 3, right, and all the way to n minus 1, right? This is a basic for loop in Java. All right, so we're going to be essentially incrementing. This is going to be incrementing n times, right? And we're running a function every time we increment, right? So we're running O of 1, right, O of 1, O of 1, and we're essentially going to be running this n times. Right? So what would be the complexity then of this for loop? Well, you might have already guessed, it's going to be the number of times the loop runs, right? Times or multiplied by everything inside of the for loop. Because everything in the for loop we're running n times, right? So, and that's going to essentially be repeating this complexity as many times as I'm running it. So in this case, the O of my entire for loop here, so if I say the O of for loop, right, is going to equal the O of n, which is the number of iterations, right? The number of time this runs. This is going to be number of iterations times our O of 1, which is going to be the time complexity of the body, right? Of the for loop body or the for loop block here. And then this is essentially going to be, well, if you just do some basic math, and the basic math rules do apply, right? This is going to be O of n times 1. This is going to be O of n. So, and I'm actually going to kind of erase this and move it because my face cam might be in the way. So this is going to be O of n right over here, right? Now, if you can imagine if I were to change this, so let's say that I'm like, all right, well, I don't want this to be O of 1 anymore. I want this to be O of n. Right? Well, I'm going to be doing the same formula. I'm going to take O of n, which is the number of iterations. Well, really, this isn't really an O. This is just n, right? Because it's just running it n times. So let's say I take n and I multiply it by the inside, which is going to be O of n. This is going to be equal to O of n squared, right? Because you take n times n. All right? Let's jump down here. Now, this is another thing. We have a for loop inside of a for loop. And we're just going to say, for the, again, sake of the example, I'm actually going to make this I'm going to make this a bit interesting. I'm going to make this O of log n here. Like, let's say my do something is O of log n, right? Well, we can look at all of our for loops. So our first for loop goes from, it goes here from 0, right, all the way to n minus 1. That we know. And so this is going to be running n times. So the outer for loop is going to run n times. So remember our formula, we have the number of times it runs, right? Or number of times it runs times the actual complexity of the body, or what's inside of the for loop. So we can start this by saying n times, well, what's inside? Well, what's inside is going to be another for loop. So we have to put parentheses here, and we need to figure out what this entire time complexity is. Well, we're running this, and I'm actually going to be changing, I know this is slightly cheating, but just for the example, I'm actually going to be changing this code a bit to say greater than 0. Let me see if I can kind of erase this. The reason is because I want to kind of make this a little bit more of a simpler example. So let's see if I can actually do that successfully. Yeah, that'll work for now. Well, if we look at this, well, we can say that we're running from n all the way to 1. And this is also going to be n times. So I'm going to have now n, which is my outer loop, the number of times my outer loop runs, times n, which is now the number of times my inner loop runs, and then remember, it's now multiplied by the body of that loop. And the body of that loop is going to be this O log of n, right? So now what you'll end up with when you were to solve this out is this is going to be equal to n times O of n log n. Remember, that's how we got that, you might have been wondering when in the world would you get n log n? We just did here. And then we calculate this again, and this is going to be here O of n squared log n. Just like that. So that's another interesting thing, right? When you have nested loops, you need to make sure that you're essentially following the same, you're following the same formula where you take the number of iterations, multiply it by the complexity of the inside, right? However, you're doing that twice because you have 2 loops. And this works if you have 3 or 4 or 5 nested loops, right? You just keep going down and you keep kind of multiplying this out. Now we look at something interesting here where we're essentially going to be combining. We're going to be combining, again, for the sake of the example, I'm going to erase this little equals here, but we now have the same loop that we had before, and I'm going to essentially say the same thing, that this do something is going to be O of log n, and then I'm going to say that this do other thing is going to be O of, let's say that this is going to be O of 1, right? Well, we know this complexity because we just solved for it above. It's the same code block. We know that this is going to be, this entire thing, right, is going to be O of n squared log n, right? But now we have another thing right below it that we need to also worry about, because this is all in the same line. So, our program is starting up here somewhere, and it's running this loop, and then it's going to run this loop. So what's the overall complexity of the entire thing, the entire code block, right? Well, in this case, let's look at the complexity first of the second loop. So we can take a look at this here, and we can say that we have from 0, we're going from 0, and we're going all the way to 2k minus 1. Remember, now we have a new variable I added here, k, right? And you see that we're essentially going to 2k minus 1, but you're adding 2 every time you're going. So in reality, you're still running this, you're going to be running this you're going to be running this n times, because you go from, 0 to 2 to 4 to 6 to 8. So it's very also important to, keep track of your increment value, and you're going to go all the way to 2k minus 1, which is going to still run n times. Well, actually, no, it's not running n times, it's running k times, right? Because remember, our variable here is k not n. So we're running this k times. So if we look at the overall complexity, well, you take k, the number of iterations, times the complexity of the inside, which is just O of 1, because we have one thing in here. So this is going to be O of 1, and this is going to be equal to O of k, right? So now what do we do about this? We have we have these 2 statements, essentially, I guess, consecutive statements, right? One follows another, and they're at the same level. Well, all you have to do with consecutive statements is you add. So for consecutive statements, you add. So we can take O of n squared log n plus OK, and that is going to be the complexity of this entire thing. Now, I would like to just show you, because remember, we're talking about parent functions. In this case, we have 2 different variables. We have n and k, so we cannot combine these. However, let's say that this, instead of k, the second loop was n, you would end up with O of n squared log n, right, plus O of n, right, in this case. And then you would probably, say O of n squared log n plus n, which again can actually be simplified all the way down, right, to O of n squared log n, right? Because we're talking about the leading term here. Okay? So that's something very important to kind of keep in mind. So this is I'm just going to say this is if the second loop uses n. And this is important because, again, we're talking about parent functions, and we're talking about here this, this max, right? This upper bound. So we're really, the leading term always wins here, and it kind of cancels out any effect of any lower terms. That's why it's always one item. And whenever you're seeing O of n described, you're never going to see a plus ever, unless, like, as a final solution, unless you're adding together the complexity of two variables, right? Even in this case, I can probably write this as O of n squared log n plus k, right? Both are essentially equivalent, so these two are equivalent values. So, you can write it either way there. All right. So now we have talked about all these different ways that we can structure our code and how we calculate, right? How we calculate the actual time complexity. So remember, a single statement, especially if it's going to be arithmetic, is going to always be O of 1, right? So this is going to be O of 1, especially, and again, this is again for arithmetic, for comparison, right? Now, remember, this can be O of whatever if our single statement is running a function, which contains a bunch of code in it, right? So this is really for arithmetic comparison, really single statements. But if you're running functions, so like if I'm running a function or a method, right, running a method, I might be referring to functions and methods very similarly, but in Java, they're mainly called methods. Other languages are called functions. So running a method, this is going to be O of something, right? Well, that looks like an N. O of something, right? Depending on the method, right? So that's something really important. Now, if you have a block of statements, right? This is meaning that you have many statements. You essentially take the O of the first statement and you add the O of the second statement, and you essentially add all the statements, right? This is what I did above, where I had two different statements on the same level and I added them together, right? So consecutive statements. Now for if statements, remember, you need to calculate the max. So you're going to take the max of the O of the condition, right? O of the condition, right? The O of the if statement, the O of also any if else, right? We didn't say if else, but any if, like any else if, I guess, right? Any else if, right? And then you have O of else. And you take the max of all those, and that's going to be the complexity of the entire if statement. For loops, you're going to have n, which is going to be the number of iterations, right, times the O of the body of the loop, right? And lastly, if you have a nested loop, you're essentially going to do the same thing, where you have, and I'll write it out again, this is going to be n of the number of iterations of the outer loop, right? And then this is going to be times the entire O complexity of the inner loop. And again, this would then refer back, right? This entire thing would then refer, like this piece would then refer back to this to try and figure out. Now, lastly, you'll notice this word here, this very scary word, recursion. And I'm actually going to be talking about the complexity of recursion in a different video, because that is a bit more complex. But this is a very good summary of kind of how to find the complexity of all these various things. All right, so if you liked the video, feel free to like and subscribe for more content. If you have any questions, feel free to leave them below, and see you all in the next one.